All right, here we go with the Chapter 3 homework review, the last homework assignment that's covered on the first exam. The average this week was 9.29 out of 12, so a little bit lower, but pretty typical for this assignment, so we're not too far off the pace. So I like to see these scores a little bit higher, but the important thing, of course, is that you're learning something from these assignments. So today we're going to go through a variety of questions. All of these were ones that I identified in Blackboard as having success rates of 50% or less, meaning less than 50% of the people that tried these questions actually got the correct answer. So these are ones that were particularly difficult, and they do cover a variety of topics that were important on this week's assignment. So the first one I'm going to deal with is involving radius, and here we're comparing atoms and ions to each other. This is sort of a holdover topic from Chapter 2, technically speaking, if we want to see where it was in the book, but some of the concepts here are certainly important to review. And when you're comparing a series of atoms and ions like this, so we have phosphorus, Cl-, aluminum, S2-, gallium, we can use a periodic table for the neutral elements in the series, but we have to think about electron configurations and some of the effects on ionic radius when we add or subtract electrons for the other ones. So for this problem, what I'm going to first do is try to compare the three neutral atoms that are on here, P, phosphorus, Al, aluminum, Ga, gallium, and figure out what order those come in. And again, we're looking for the smallest one here, so we need to figure out which of these three is the smallest, and then we'll have to compare that one to the two anions in the series. Okay, so if we go through to the periodic table and look for those three, P, Al, Ga. All right, so if we have phosphorus versus aluminum, phosphorus is to the right of aluminum. Remember that radius is going to decrease left to right for neutral atoms. So as we go from aluminum to phosphorus, we're going to decrease. That means phosphorus is smaller than aluminum. Then if we compare phosphorus to gallium, gallium is both to the left and below phosphorus in the periodic table, so in those both directions is largest. So of those three, Ga, Al, P, gallium is the largest, then aluminum, then phosphorus as we go again, bottom to top, left to right. Okay, so this is gallium, then aluminum, then phosphorus. So of those three neutral elements, phosphorus is the smallest. That's the only one we need to consider from now on. So this is the smallest of those three. The order would be exactly as written here. All right, so that's the order for those three. Now we have to compare phosphorus versus Cl- versus S2-. When you're comparing an atom to an ion, the first thing to think about is which subshell are the valence electrons in. So if we go to the periodic table and look at those, phosphorus has its valence electrons in the 3p subshell. This is the 3p part of the periodic table. S2-, it has more electrons, but it's still 3p. And then Cl- also 3p. So we basically have three elements that are all 3p. Now the key point here, though, is that these are all 3p valence electrons. And when you're comparing neutral atoms versus anions that all have the same valence shells, anions are much larger than the neutral atoms. All right. So there's some effect of moving left to right in the periodic table. So if we go phosphorus, Cl-, S2-, Cl- is the furthest to the right, but it's an anion compared to phosphorus, which is neutral. And so basically, if you have these three things all in the same row of the periodic table, the ones that are anions are going to be the largest. Cl-, S2- probably fairly similar in size. S2- probably a little bit bigger because it's a 2- anion, as we talked about. So these two are isoelectronic. So this one we know S2- is larger. Here, I'll circle a smaller one. So if we do Cl- versus S2-, Cl- is smaller because it's only a -1 anion versus -2, and these are both 18 electrons. And then if we do Cl- versus phosphorus, they don't have the same number of electrons, so we can't just use the isoelectronic comparison, but they're both 3p. This one is negatively charged, this one's neutral, and so we expect the neutral one to be smaller. And if you look at the real numbers, you don't have to look these up for this problem, but phosphorus has a radius of like 110 picometers and Cl minus is like 184. So just adding one extra electron to the outer valence subshell has a huge effect on the radius. And so anytime you're comparing anions with neutral elements, if they're in the same subshell, the anions are going to be much larger than the neutrals. So that leaves phosphorus here as the correct answer, is the one that's the smallest, because compared to the two anions, which are also in a 3p subshell, you expect the neutral to be smaller. All right, this next one here deals with polar bonds. Here we're looking for least polar bond among the following. And what we're doing for these ones, remember that for bond polarity, the key parameter is difference in electronegativity. So you have two atoms bonded to each other, and how far apart the electronegativity values are is going to determine how polar the bond is. All right. So some of these are not as obvious as others in this, but if we look at the answer choices here, we're looking for the least polar bond. What's helpful to remember is that carbon and iodine have the same electronegativity because these two are far apart. So we have, we're comparing a lot of different bonds here: CO versus SiH versus ClF, CF, Ci, and so on. So some of these are going to be hard to compare to each other, but one thing that's helpful is that carbon and iodine have the same electronegativity. So they're far apart on the periodic table. Electronegativity increases as you go left to right, then it decreases as you go top to bottom. So to go from carbon and iodine, you go over 3, 1, 2, 3, you go down 3, 1, 2, 3, and it turns out those are about the same as each other. So we would expect then, even though it's not obvious necessarily from their position on the periodic table, that this is basically a nonpolar bond. Now the rest of these, we want to verify that they're also, then are they polar or nonpolar. So if we go CO, this is a very polar bond because the electronegativity difference between oxygen and carbon is significant. So oxygen is the second most electronegative element, and it's going to be way more electronegative than carbon. So you're going to have a delta electronegativity of around 1. If we go to choice B here, which is SiH, this one is not terribly obvious also. One thing that's helpful to remember about hydrogen, it's way over here on the periodic table. It's sort of grouped with the metals, but it actually is a nonmetal. So its electronegativity value is not, it's sort of what I would say an intermediate value. So it is helpful to remember that the electronegativity of hydrogen is the same as phosphorus. So it's a little bit less electronegative than carbon, a little bit more electronegative than silicon, so it's sort of in between those two. And so if you have a silicon-hydrogen bond, like we do in choice B here, it's going to be a little bit polarized towards hydrogen, but I would say not very polar, but a little bit polar. All right, so it's helpful to remember some of these benchmarks because some of the elements, especially hydrogen being the one that's key here, they're not in the most obvious place in the periodic table, so you have to help kind of just benchmark their electronegativity. So hydrogen is a little bit less electronegative than silicon. It's in between silicon and carbon. If we go to ClF, a lot of you picked this answer choice, and this was not a bad choice. Cl and F are fairly close to each other in electronegativity, but it still would be a polar bond. Fluorine is the most electronegative atom on the periodic table, so it's going to be more electronegative than chlorine. You're going to have a polarized bond towards fluorine. Again, not terribly polar because they're fairly close to each other, but still significantly polar. Then if we go to choice D, which is CF, this is going to be a pretty polar bond because there's a large electronegativity difference between fluorine and carbon, being about 3 columns apart in the periodic table. So you have a pretty big pretty big increase in electronegativity as you go from carbon to fluorine. So the only one that looks like it's going to be the correct answer, which again, this is not the most obvious, but I understand why a lot of us got this wrong, is that choice E, Ci, is going to be the least polar bond because carbon and iodine have basically the same electronegativity. Electronegativity for carbon is around 2.1, the same with iodine. I believe they're about the same on the Pauling scale, which means that the difference in electronegativity between these two is 0. So Ci bond, even though the atoms are kind of far apart from each other in the periodic table, that's basically a nonpolar bond. The rest of these are at least a little bit polar. SiH is pretty nonpolar, but still a little bit polar, and same with the rest of these. They all have some polarity. So the one that doesn't have a difference in electronegativity, and thus is basically a nonpolar bond, is going to be choice E. All right, the next three questions deal with Lewis structures, or Lewis dot structures as they're sometimes called. And they're asking us different questions about formal charge and things of that sort. So this first one deals with the compound thionyl chloride Cl2SO. We're telling you here that S is the central atom in case that wasn't obvious. And we want to know the formal charge and number of lone pairs on sulfur. And the key point here is that we assume all atoms should obey the octet rule. That's a typo there, which hopefully didn't cause you any confusion. But we're assuming that all atoms obey the octet rule in this structure, which is something we have to point out here because the central atom is sulfur, and sulfur is in the third row of the periodic table. So sulfur can expand its octet. Here, we're telling you that it's going to obey the octet rule, so we don't want to do that. So anytime we say obey the octet rule, we want to make sure that no atom in the structure has more than 8 electrons around it. And ideally, they should all have exactly 8, with very few exceptions. Okay. So if we draw this Lewis structure, Cl2SO, Cl is going to be a group 7 element, so it's going to contribute 7 valence electrons. Sulfur is in group 6. And then oxygen is also in group 6. So this is going to be 26 valence electrons in this structure. So if we do Cl2SO, we put sulfur at the center as the problem tells us to do. We do single bonds to the oxygen and the 2 chlorines. We're going to start by completing the octets on the outer atoms, chlorine and oxygen. So in doing that, we've used 3 octets. We have 3 complete octets now, 1 oxygen, 2 chlorines. That's 24 electrons. We still have 2 left out of our 26 total, which means we're going to put a lone pair on the central atom here. All right. So that part's not going to change. We know that there's 1 lone pair on the central atom on the sulfur. So that's one part of this question here that we can answer now. But we have to calculate the formal charge. So the first thing is to make sure that this structure obeys the octet rule. We completed the octets of all the outer atoms, and now by putting this lone pair on the central atom, it also has exactly 8 electrons. 2, 4, 6 from the bonds, 2 more as lone pairs, as non-bonding electrons. That's a total of 8 electrons. So everything obeys the octet rule, so we don't want to add any more double bonds or anything to this structure. So we can just calculate formal charge of sulfur here. To calculate formal charge, we start by taking the number of valence electrons that the atom has, which is 6 for sulfur. We subtract the number of bonds that it has in the structure, which as drawn here is 3. And then we subtract the number of non-bonding electrons, which is 2. These 2 non-bonding electrons, and that gives us a +1 formal charge in sulfur. So when we calculate formal charges in this molecule, we get +1 in sulfur and -1 in oxygen if we did that one. So we could, in principle, draw a double bond to get rid of the formal charges, but that would require us to expand the octet in sulfur, and this problem specifically wants us to obey the octet rule. So as I said, we're going to stop with this structure here. We've determined that there's a +1 formal charge. We've determined earlier that there's just 1 lone pair. And so the correct answer for this is going to be choice A. +1 formal charge, 1 lone pair. Read the question carefully because here we're looking for a number of lone pairs on sulfur atom. There's 1 pair of electrons in sulfur, even though there's 2 total non-bonding electrons. So a lot of people picked choice E here, and they probably did that because they thought we were counting these electrons individually, but we're looking at pairs of electrons in sulfur. So make sure, again, you read the question closely because sometimes we'll ask you to count electrons individually. Sometimes we'll ask you to count them as lone pairs, as we did here. And so in this case, there'd just be 1 lone pair on the central atom. The next question here deals with the formal charge on nitrogen for nitrite, NO2-. In this one, we don't specify anything in the octet rule, but we don't have to because nitrogen and oxygen, the 2 elements in this formula, they're both 2p elements, which means they cannot go beyond 8 electrons. They should ideally have exactly 8 electrons. So we're not going to expand the octet in this structure no matter what because the elements that are involved cannot go beyond 8 electrons. So to do the Lewis structure for this one, we're going to follow the same approach. We have nitrogen and 2 oxygens and a negative charge in the formula. So we have nitrogen is group 5, so it's going to contribute 5 valence electrons. Each oxygen contributes 6. They're from group 6. Then we have one negative charge, which adds one more electron. So we have a total of 18 electrons in this formula. And so if we go NO2 minus, we go with single bonds to each oxygen. We complete the octet of each oxygen. So that gives us 2 times 8, which is 16 valence electrons used up so far. Then we have 2 more out of our 18 that are left. Those go on the central atom nitrogen. So looking at this structure here, though, we'll see that right now our nitrogen only has 2, 4, 6 electrons. 4 from the 2 bonds, 2 more as a lone pair. So this only has 6 electrons in the central atom, so we have to fix that. Remember that the way that we can fix that is by drawing a double bond. So we're going to take off one of our lone pairs from oxygen and make a double bond. In principle, we could have done this with either oxygen, so in reality there's 2 equivalent resonance structures for this, where we can put the double bond on either side. So we could also draw it with this, where there's a single bond there and then a double bond to the outer oxygen. But in both cases, one lone pair on the nitrogen, and the formal charge on nitrogen is going to be the same for both of these. So it doesn't matter which. If you draw only one of them, you'll be fine. So to do the formal charge on nitrogen, once again, we're going to start with the number of valence electrons that nitrogen has as a free atom, which is 5. We're going to subtract the number of bonds. Whichever Lewis structure you use, nitrogen has 3 bonds, 1 single and a double, so a total of 3 bonds. Then we're going to subtract the number of non-bonding electrons, which is 2, so the nitrogen will have 0 formal charge. So as long as you complete the octet of nitrogen, which you have to do to make it a good Lewis structure, the formal charge will be 0 no matter which Lewis structure you draw. So the correct answer for this would be choice C. All right. And then finally, this question here asks us, which of the following contains carbon with a negative formal charge and is most important Lewis electron dot formula? So in other words, if you draw the structure of these compounds or ions, and you obey the octet rule and follow everything, which one will have a negative formal charge on carbon? It's actually a pretty rare situation to have a negative formal charge on carbon. Carbon very rarely has formal charges at all, as it turns out. But as you'll see, there's going to be, one example in this one that does have negative formal charge. So if we look at all these answer choices, we have to draw Lewis structures that obey the octet rule, and then we're going to have to calculate formal charges. I'm not going to go through all the steps, but what you would get, and if it's good to review this on your own if you want to go through all these in more detail, but basically for CO, you would get a structure that looks like this. We did this one during the review on Friday if you followed along with that. So CO is sort of a weird one because it has a lone pair on carbon, which is not very common. And if we calculate the formal charge on carbon, we get carbon is in group 4, so it have 4 valence electrons. It has 3 bonds in this structure, and it has also 2 non-bonding electrons. So that's going to give us then a -1 formal charge on carbon. So that's actually going to be the correct answer here is CO, which has a negative formal charge on carbon. And this is the only way to arrange the electrons that completes the octet. So it's weird to have a negative formal charge on carbon. It's also weird to have a positive formal charge on oxygen, but there's the only way you can do this to complete the octet in this structure. So that's our correct answer. Let's go through the rest and just verify that they don't have formal charge on carbon. So for CO2, you get 2 double bonds. And then each oxygen has 2 lone pairs. And if we calculate the formal charge on carbon for this one, 4 valence electrons, this time 4 bonds, and 0 lone pairs. We said during the review session that a helpful shortcut is that for 99% of Lewis structures involving carbon, carbon has 4 bonds and 0 lone pairs, and if that's the case, then it'll have 0 formal charge. So CO is sort of a weird exception to that. If we go to CO3 2-, there's a few resonance structures we can draw, but they all have the same formal charge on carbon. So carbonate, which is what this anion is called, as you should remember, has this Lewis structure, and the formal charge on carbon, 4 valence electrons. This one also has 4 bonds and 0 lone pairs, so it's going to be 0 for that one. CH3OH, you get this thing here, where again, helpful shortcut, carbon wanting to form 4 bonds, oxygen wanting to form 2 bonds and 2 lone pairs. And the formal charge on carbon in this case is going to be 4 valence electrons, 1, 2, 3, 4 bonds, and then 0 lone pairs, so also 0. And then finally, choice E, which is HCO2H. This is a bit of a weird one. It's going to be HC, and then you have, so whenever you see CO2H, which is a common part of an acid, it's going to be sort of this thing here. C with a double bond to an oxygen, and then a single bond to an OH. But at any rate, the formal charge of carbon on this one is going to be 4 valence electrons, 1, 2, 3, 4 bonds. I should keep the lone pairs on oxygen to be complete. But 4 bonds on carbon, and then no lone pairs on carbon, so it's going to be 0. So all the rest of these have a formal charge of 0 on carbon, which is the most common situation, but choice A does have a negative formal charge. That's the only way to arrange the valence electrons for that Lewis structure. All right, so this one here, we're dealing with which of the following combinations of names and formulas of ions is incorrect. And a lot of you, I think, got the wrong answer just by not really looking at the answer choices closely. So for most of these are anions. The exception is choice B here. So remember that when we're naming a metal cation, it's just going to be the name of the metal, and then if it's a variable charge, you have to put the charge in parentheses. But aluminum, if you look at aluminum on the periodic table, this isn't the most obvious one, but aluminum is here in group 3. It's a S2P1 valence configuration. And so for aluminum, it's always going to make +3 cations. It's going to lose all 3 of those valence electrons to get to the neon electron configuration. And so aluminum is always +3, meaning you don't have to indicate its charge in parentheses. And that means that the aluminum +3 cation would just be named as aluminum. So that's the only metal cation in the list, and that's correct. When you're naming metal cations, remember that they just keep the name of the metal, although for transition metals in particular, we need to put the charge in parentheses to indicate that it's a variable charge. But for the rest of these, you have to look at this. So choice A is the one that a lot of you missed, but it's written as O subscript 2 minus. So basically this would be O2 with a negative charge, and this one would be called, it's not the most common one, but it's called superoxide. Okay? Oxide would be O with a 2 minus charge, meaning the 2 and the negative are both superscript, meaning that it's a -2 charge. This would be oxide. That's the common one, which is just oxygen gaining 2 electrons. But here the 2 was given as a subscript, meaning that what this actually is it's an O2, a polyatomic ion, an O2 molecule with a -1 charge, not one that we're likely to encounter. I'm not even sure if it's on your list of anions that you need to know. This one will be called superoxide, but it's certainly not oxide, because oxide would be O2 minus with the 2 minus superscripted. So that's the one that's going to be incorrect. The rest of these are fine. So choice C, NO3 minus nitrate, that's correct. PO4 3 minus phosphate, CrO4 2 minus chromate. These 3 you're going to have to learn your polyatomic ions to be able to know those and verify that they're correct, but they are indeed the right name and formula and charge for all of those. All right, so for that one you need to know your polyatomics, but also have to look really closely at the way that the formula is written for choice A and recognize that it's not a -2 charge. That's a subscript 2, indicating that there's 2 oxygens and just a 1 minus charge. All right, this one's a little bit out of order. I should have probably put this earlier. But we need to know which of the following covalent bonds has the highest percent ionic character. So remember that highest percent ionic character is the same way as saying most polar. Okay, so there's a couple different ways of saying that, but percent ionic character is just a synonym for polarity. So if you want the highest percent ionic character, you're looking for the most polar bond. These all involve carbon, and so to find the one that's the most polar, we just have to compare carbon to the other atom and see which one's furthest apart in electronegativity value. So if we go CO versus CCl, before we do that though, let's look at if there's any that we can eliminate. And what we'll see right here is that choice C is carbon bonded to itself. This one is going to be perfectly covalent, and thus it's going to have 0% ionic character. So anything that's the same atom bonded to itself, or 2 atoms with the exact same electronegativity, as can sometimes happen, that would be a nonpolar bond, or it would have no ionic character. So choice C we can get rid of because it's a completely nonpolar bond. Here we're looking for the one that's the most polar. But for the rest of these, we're going to have to compare. So if we go CO to CCl, this one, again, it's not always the most obvious. So oxygen versus chlorine, they're both more electronegative than carbon. The question is, which one is a greater difference? So you notice that to go to oxygen, we go 2 to the right. To get to chlorine, go 3 to the right and 1 down. So which of these is more electronegative is not obvious based on their location. So this is where it's helpful to remember the top 3 electronegativity values, I think, just to be able to help orient yourself. So fluorine is the most electronegative, then oxygen, then chlorine. So those atoms are the most electronegative. So oxygen and chlorine are 2 of the 3 most electronegative atoms. But oxygen is more electronegative than chlorine, meaning that the polarity of a carbon-oxygen bond is larger than the polarity of carbon-chlorine. They're both more electronegative than carbon, but the difference between carbon and oxygen is thus greater because oxygen is a bigger electronegativity value than chlorine. Okay, so comparing those two, CO is going to be more polar, so we can get rid of choice B. If we go CO versus CH, again, not super obvious from the location on the periodic table, but as we talked about in one of the earlier questions, hydrogen, even though it's way over here on the left, it is a nonmetal, so its electronegativity value is not super low. And hydrogen is basically the same electronegativity as phosphorus. It's sort of in between carbon and silicon. So a carbon-hydrogen bond is going to be a little bit polar. Carbon is a little bit more electronegative than hydrogen, but it's not very polar. So something that'll be an important topic in organic chemistry if you take that. CH bonds, carbon-hydrogen bonds, are mainly nonpolar, just a little bit polarized. And so if you're comparing carbon-oxygen to carbon-hydrogen, there's a big electronegativity difference between carbon and oxygen. There's a very small electronegativity difference between carbon and hydrogen, so carbon-oxygen will definitely be more polar. And then finally, carbon-oxygen versus carbon-nitrogen. We can write the atoms in either order. Again, nitrogen and oxygen are both more electronegative than carbon, but oxygen and carbon are further apart left to right. So these 3 are all in a row, so the electronegativity is going to increase as we go from carbon and nitrogen to oxygen. The bigger difference would be between carbon and oxygen versus carbon and nitrogen. All right, so that's going to be our biggest difference, which means of all of these bonds, the carbon-oxygen bond is the most polar or has the highest percent ionic character. So the only other bond that would be more polar than this that involves carbon would be carbon-fluorine. And that's where it's, again, helpful to remember the top 3 electronegativity values. All 3 of these are going to be covalent bonds, but then the carbon-fluorine would be the most polar, but that's not one of our answer choices here. Carbon-oxygen is the next most polar bond, covalent bond involving carbon, and then carbon-chlorine. So that's those are helpful things to remember. All right, the last one we want to go through here is the bond energies of X2 and CX are 156 and 257 kilojoules respectively, and the bond energies of CC and single and CC double bond are 338 and 604 kilojoules respectively. Give an estimate of delta E for the reaction below. So the key to doing this question is we have to be able to draw Lewis structures of the reactants and products to make sure that we have the correct number of bonds and the correct bond order. So when you see a formula like C2H4, the way that you're going to do it is you're going to draw a bond between the 2 carbons, and you're going to distribute the hydrogen atoms evenly. So if it's C2H4, you're going to assume that there's 2 hydrogen atoms on each carbon. And the shortcut that we talked about in the context of Lewis structures is that carbon is going to tend to have 4 bonds in its Lewis structures and no lone pairs. So in this structure here, C2H4, to be able to satisfy that, we have to have a double bond between the 2 carbon atoms. So C2H4 is going to be a CC double bond. And that's going to combine with X2, which we gave you the bond energy of just X2, so we're going to assume that there's a single bond. It doesn't really matter what it is, we just gave you 1 bond energy. And then the product here, C2H4X2, again, we're going to distribute everything equally. So it's going to be 2 hydrogens and 1 X on each carbon. C2H4X2, 2 hydrogens, 1 X on each carbon. In this case, the carbons already have 4 bonds, 1, 2, 3, 4, so we're going to leave it as a carbon-carbon single bond. We don't want to have any more than 4 bonds per carbon. That's what they refer to as a Texas carbon. So now we have the Lewis structure sketched out, and so we can go through and start tabulating the bond energy. So on the reactant side, we're going to break all the bonds. So this first reactant has 4 CH bonds. Now here we didn't give you the CH bond energy, so we're going to have to leave that as just 4x, whatever. So x is going to be the CH bond energy. As you'll see at the end, we don't need it, which is why we didn't give it to you. But if you want to leave this as just x, we can do that. On the reactant side, we have a CC double bond. And so the CC double bond is going to be 604 kilojoules. And then we have one X2 or one XX bond energy. The XX bond energy is 156 kilojoules. So that means the sum of the bond energies for reactants is going to be 4x, where x is the bond energy of the CH bond that we don't know, plus 604 kilojoules plus 156. So that's going to be, if we add those together, 760 kilojoules. So it's 4x, 4 times the CH bond energy, plus 760. Let's see if I can figure out how to add a page. All right, so I was able to add another page, give us some more room to work here. So we're going to do the same thing on the product side, calculate up the bond energies on the product side. In this case, we just have one product, but it has a lot of different bonds in it. So it's going to have still 4 CH bonds, 1, 2, 3, 4. And before we called the CH bond energy X, we don't know what it is. In the product side, we have 2 CX bonds. So whatever this X atom is, we have 2 bonds between carbon and X. So that's going to be 2 times, we said CX is 257. $514. And then we also had, remember, our CC single bond. So the carbon-carbon single bond energy is this one here, 338. All right, so a lot of different bond energies in this question to keep straight. And then we have one that we don't know, as we said, which is CH. So when we add up on the product side, the sum of the bond energies is going to be 4x, which is the 4 times the bond energy of CH that we didn't know, plus 852. And then finally, to get the delta E, remember it's going to be the sum of the bond energies of reactants minus products. So it's going to be 4x plus 760 kilojoules minus, and then we have 4x plus 852 kilojoules. And what you'll see is because we had 4 CH bonds on each side, the unknown 4x, the bond energy of CH, cancels out. So in other words, we're not changing the number of CH bonds that we have between the reactant over here, which has 4, and the product, which also has 4. So the CH bond energy doesn't matter because we're going to break 4 CH bonds on the reaction side, but we're going to form 4 on the product side. So in net, that's no change. So that unknown part cancels out, and we're just left with a numerical answer that's going to be negative 92 kilojoules. All right. So this would be the correct answer for this one, entered in whatever format Blackboard specifies, which is probably just minus 92. So even though we didn't tell you the bond energy for the CH bonds, that may have caused some confusion, but we didn't need it here because it cancels out 4 CH bonds on the reactants, 4 CH on the product. And the only thing that's changing is going to be the CC bond order as well as the number of CX and XX bonds that we have. All right, so that takes us to the end of this week's review. A lot of different questions related to covalent bonding and nomenclature and things of that sort. So if there's any other topics you want to go over with me, please let me know. And we're going to be Again, moving through the exam this week as well as going through some of the Chapter 4 topics in class. So I'll be back next week with a homework review on Chapter 4.